Okay, so today what I would like to do is start to go over covalent bonds. So before we get into covalent bonds, I want to just compare and contrast ionic and covalent bonds. In both situations, atoms are trying to achieve a noble gas configuration. The difference here is that they're going about it a different way. Remember, with ionic bonds, we have metals bonding with nonmetals, and the metals are transferring an electron to a nonmetal to form oppositely charged ions, which are attracted to each other. And with covalent bonds, this is going to occur between nonmetals. And what we actually have here is we're sharing electrons to achieve that noble gas configuration. So, like I said, with covalent bonds, this is resulting from the electron pairs being shared between both atoms, two atoms. And the thing that you need to remember here is electrons shared belong to both atoms. So a lot of times when covalent molecules are drawn, they're drawn so that the electron clouds surrounding particular atoms kind of overlap all the atoms in the structure. So, what we also see is that a lot of times it's not going to be very black and white. We're not going to have just an ionic or just covalent. Sometimes it's going to be kind of in between. So, we're going to be looking at electronegativity and the difference in electronegativity. And what you will see is that if the electronegativity difference is less than or equal to zero point 0.4, we have what we call nonpolar covalent bonding, where electrons are being shared equally between the two atoms. If the electronegativity difference is between zero point 0.4 and 2, what we have here is polar covalent bonding, where the electrons are shared unequally. If the electronegativity difference is very large, that is, if it's greater than or equal to 2, what we have here is ionic bonding, where electrons are being transferred from one atom to the other to form ions. For covalent bonding, the electron cloud surrounding the two atoms is very symmetrical because electrons are being shared equally. With polar covalent bonding, what I want you to see here is the electron cloud is very asymmetrical since electrons are being shared unequally. So what I want to show you with this analogy here is when we think about a polar covalent bond, what's happening here is that the more electronegative atom, in this case fluorine, actually ends up with electrons more of the time. And this is what causes the cloud of electrons to be asymmetrical and for there to be more of an electron density over the more electronegative atom than the less electronegative atom. So these two atoms end up sharing the electrons, but the more electronegative atom, like I said, gets the electrons most of the time. The less electronegative atom does have the electrons also, but only some of the time. Okay, so we're going to be using this table of electronegativity to predict what kind of bond we have. So I'm going to bring up the worksheet that's on Google Classroom so we can practice with some of these. Okay, so we're going to be looking at this sheet. This is on Google Classroom, and you should pull up a copy of this. But what I want to show you at the top here is our table of electronegativity. So we're going to be using this to evaluate these different bonds. So when you're doing these, what I want you to do is I want you to look at the two different elements you have in your compounds. So let's do the first one. Here we have carbon and hydrogen. So don't worry about the fact that there are four hydrogens or there's one carbon. Just look at the electronegativity values for those two elements. So if we go to the top, what we see is carbon has an electronegativity of 2.5. So I'm going to write that down. And hydrogen has an electronegativity of 2.1. So here we have carbon, 2.5, hydrogen, 2.1. So the difference between those is 0.4. So this tells us that we have a nonpolar covalent bond. So since this is a nonpolar covalent bond, there's not going to be a slightly positive or slightly negative end with our bond. So we're just going to leave it like it is. Now, if we go to sodium chloride, we look at the top here, we see that sodium has an electronegativity value of 1.0. Chlorine has an electronegativity value of 3.0. So we have 1.0, 3.0. So the difference here is 2.0. So this would be an ionic bond. Now, you could think about chlorine is stealing an electron away from sodium. So chlorine should end up with a negative charge. And we know that from a periodic table. Sodium should end up with a positive charge. So that's what we would write for a notation there. So now let's look at phosphorus and hydrogen. So actually, let's not do phosphorus and hydrogen, but nitrogen and oxygen. So we see here nitrogen has a electronegativity value of 3. Oxygen has an electronegativity value of 3.5. So nitrogen is 3, oxygen is 3.5. The value here is 0.5. So we see here that this falls into the polar covalent bond. So here, since oxygen is more electronegative than nitrogen, it's going to pull those electrons toward itself. So it's going to end up being slightly negative. So this sign here is delta. This is another Greek letter, and this just stands for partial. So it's a partially negative end, and this end is partially positive. Okay, so I want you to try these on this sheet. Make sure you understand what you're doing, and then we'll proceed from there.